minus 3 and plus 3 sigmas is 99%. And for many purposes, 99% is good enough. However, there is a logistical movement called 6 sigma. Maybe you've come across it, 6 sigma. And 6 sigma actually extends this to even further to 6 sigmas, both on this side and that side, and 6 sigmas is 99.9999999%. So literally everything. But for the moment we will be talking about minus 3 and plus 3 is together 6. Okay?
Just, you sort of lost me there, to be fair. So you said 68% is the value of 68% of the mean.
No, 68% of all values that come from our sample will be plus or minus 1 sigma.
So it'll be between that.
That's correct.
This. We just shade the area, that would make it
correct.
For example, yeah. So between this and this shit.
That's 6 sigma. Okay. Now what we have to do is when we set our machinery is we have to make sure that our design specs, our tolerance levels, cover 6 standard deviations. Because when they cover 6 standard deviations, they cover 99% of all output. Okay?
I'm sorry, I'm kind of catching up. What's the 95 and 99%?
That's
95 seconds.
plus 2 or minus 2 standard deviations, plus 3 or minus 3 standard deviations.
Plus 2 and minus 2 is 95 and then 99.
Correct.
Okay.
Yeah.
Plus 2.
Everybody with me?
So 99 is plus or minus 3?
3. That's correct. And because 99% is for our purposes is good enough, what we have to make sure is when we set a machine, we set a level, for example 1000 beans, we also set tolerance level. Okay? A tolerance level. And the tolerance level is the level at which we will still accept a can of beans that has not 1000 but has a bit less or a bit more. I'm just using the can of beans.
Is there like a margin of error?
It's like a margin of error. It's the tolerance level, the range at which we will not reject the output of the machine. Okay. Now, to set that level, we use 2 concepts called lower spec limit, upper spec limit. So we do this, and this is our lower specification limit. This is our upper specification limit. Okay? So when we set a machine, we have a value, we call it the design spec, and we have a tolerance level, plus or minus, which again defines our lower spec level and our upper spec level.
Is that written down as LS2?
No, that's USL, upper specification limit. Okay. And this is the lower specification limit. Okay? But here's the trick. We need to make sure that that tolerance level is at least 6 sigma. Because if it is at least 6 sigma, it means that 99% of all output will fall within the tolerance levels. Does this make sense?
Yeah.
No.
Yes,
What do you mean by 6 sigma?
6 sigma is the, if you like, the spread of the
Okay, so
normal
we have to watch
distribution.
for 6 numbers outside of the median.
No, it's 3. So minus 3 sigma plus 3 sigma.
Okay, so it's
It's 6
using
sigma.
the 99%.
That's correct.
Okay.
Yeah.
Anything between the high 3 and low 3 is
Okay, so once again,
So if you set
we have to make sure when we set the limits of our spec.
you have to make sure it's between 6
Can I have your, sir? Can I have your
Sorry.
When we set the specs, we have to make sure that at least 6 times standard deviation is covered within that tolerance level. If it is not, we get something like this. Okay, so here is my output, and I set my specs by tolerance level like this. Okay, too narrow, because a lot of the output that will come from the machine will be rejected. Okay, so I have to set, or I have to make sure that if I have the output of my machine, then I set a bit like this, right? So 6 sigma. Clear?
Yes.
Okay. Now, first number, CP. You might probably think, oh, where's this going? It's going to the number CP. CP gives us an idea of whether our tolerance level is actually higher or lower than 6 sigma. And it is easily defined. It's upper specification limit that we have set minus lower specification limit over 6 sigma. That's it.
Is that the formula of work in CP?
That is the formula of CP.
For 100% of inspection.
No, that is to do with our
Tolerance.
And
statistical process control.
how do we know what the USL or LSL is?
It's a given. So
Okay.
basically you will get it in the exercise. The exercise will say this is the upper specification limit.
Is it always given, yeah?
Yes.
Okay.
Yes, because it's a design spec.
For example, when on this case, what would 6 sigma equal to? Is it the value?
Yeah, so we have to calculate standard deviation, and it's just that's a measure of the spread of the normal distribution. So in terms of, just to give you an example, this
Yes.
is, it could, what could it be? Let's say sigma is 200. Okay, so it's just a measure of the spread of the normal
So
distribution.
6 will repeat 6 and 2. 7.
Sorry, I
But
don't.
this is just an example.
Are we
Before
given
people
sigma?
start to ask where
Are we
does this
given
come from?
sigma?
I just made it up. Okay.
Are we given sigma in the exam?
Yes.
Ah, that's okay then.
See?
So would the sigma be, for example, so if there's 1,000 as the mean?
I'm going to return to this particular formula very quickly. USL minus LSL is the tolerance level. 6 sigma is the level of our distribution. I want to move on to the interpretation. What if CP is larger than 1? What does it mean?
Screwed.
It means that our tolerance level is larger than 6 sigma. Is that good or bad? That is good.
Good.
Okay, so everything that is larger than 1 is okay. If it is equals 1, what does it mean?
It's okay still.
It means it's exactly, right?
It's
So
exactly perfect.
it's really tight. And if it's smaller than 1,
You have a problem.
Good.
you have a problem because we have set our specs within the 6 sigma limit. Okay? So ideally, when we calculate CP, we look at the number we want it to be larger than 1. And it's just a measure of the spread. So that is called CP. And it's basically, we have,
You don't know?
it's just a number.
It's just like this.
It's called CP and it means a capable process.
How can we
Okay.
distinguish between the first CP that's 100% inspection and this?
Oh no, don't worry about the 100%
So
inspection.
just
There
forget
is-
about that.
Yeah, that's just to say that there are 2 types of quality control. And if we do 100% inspection, we don't need all this.
Yeah.
Okay, so,
A typical question like that,
yeah,
you'd be given the data, the 3
That's right.
sets of figures.
that's right.
So my question is, what's the point of the graph? What does the graph thing come in?
Yeah. So this graph is,
Yeah.
this is a frequency chart.
So what would you use it for?
So this is output.
You use it for the formula, right?
Yes, use it for the formula.
Yeah.
I just have a simple question to ask you, just to
Yeah.
clear my confusion. Like, you know how you say over there 6 sigma, and you
Yeah.
just gave us a random example? Could you just give me one more example to show me how to calculate that part? Because I understand the first bit, just the second one. I'm a
Sigma
bit
is,
confused.
so just like 1,000 is just a number for the mean.
Yeah,
So sigma is just a number for the variation around the mean.
okay.
So I just gave the number 200 if you're more comfortable with the number. But I could just given you any
Any.
number. It's just a measure of spread around the mean.
Okay.
So would the mean plus 1 sigma in that case be 1,200 then?
That's correct.
Okay.
Yes.
So
Yeah. The only thing,
very good. That's going to come in handy.
It's one of our topics.
Okay.
the only thing that we haven't talked about so far is CPK. CPK is a little bit more interesting measure because CP only gives us an idea of the tolerance level, whether it's wide enough or narrow enough. Just to give you an example, here is a normal distribution. Here is a tolerance level. And we might, for example, say CP larger than 1, which means it is larger than 6 sigma, which is fine. Okay. Now we have here the same thing, same tolerance levels, but the normal distribution is actually a bit out of sync. So it's a bit like here, this way. Okay. CP would still be the same number. Would still be the same number, which is not good. We want to know whether it is exactly in the middle. Exactly in the middle.
Okay.
And for that we need to calculate CPK. When CPK has to be 1. CPK has to be 1. If CPK is not 1, then the normal distribution is either shifted to the left or shifted to the right. Okay, so CPK will have to be exactly 1. That is on page 446.
So is it just basically how the spread is measured across the mean?
Yes. Okay. So here CPK is equals 1 because it's exactly in the middle. And here CPK is unequal to 1 because it's shifted to the right. Okay. So when we look at CPK, we have to make sure is it 1 or not, or is it close to 1? Yes or no? And we calculate CPK.
Oh my. No, man.
Great.
Oh no.
Okay, it's just a slide. How do we calculate CPK? CPK, we look first at CP. So we have the number here, CP. But we multiply it with a factor K. Okay? So 1 minus K.
So what's the K?
How do you calculate K? You take the difference between the design spec and your process average. Now your process average is when you take the sample, you calculate the mean of that sample. That is your process average. We'll do an example in a minute. Okay? So we can calculate CP. And we divide that by the specification range. The specification range is just the tolerance level. Okay? Okay, we're doing great. Okay, what we're going to do now is I'm going to give you an exercise, a very typical exercise. I give you all the numbers, and the idea is very simple. You calculate, first of all, you calculate sigma, then you calculate CP, and then you calculate CPK. Okay? So that's what I'm going to do now. So first, we're going to, yeah. This is the problem.
Oh my god.
What is this? It is a machine, produces bars, steel bars. So picture a machine, it just goes bars. Okay? Every time, every day, people take 5 bars.